So particles are captured within the filter media. Unlike surface filter, depth filter do not form a cake, but trap particles within the depth of the filter material. How does it work? The gas flow through a mass of randomly arranged fibers or granular material. Particles are trapped, either collide by the fibers material due to inertial diffusive electrostatic force, and the efficiency depends on the depths of the filter media and the properties of the fibers. So basically, you do have your target over here in red, and then the particles will go around and will go around. And then once they are going, we're going like this, you will have some of the particles that will be attracted to the filter itself. They either collide with it, they either hit it, or they are drawn to it with electrostatic forces, or they find their way just to the surface, and so on. So if we look at this curve over here, we have on the x-axis something called separation number, and this is really important when we are looking at depth filters. And on the y-axis, we have what we call target efficiency. So at different separation numbers, you can get different target efficiencies, and you can see that based on the shape of your depth filter of the particle of the collector in your depth filter, you can have different target efficiencies. So cylinders are a little bit less than spheres, are a little bit less than ribbons. So what are the key equations? We have the force y drag that's equal to 3 pi mu d Vy gas minus Vy particle. We have the Fy inertial, which is Ma, which is pi over 6 rho d cube dVy particle over dt. And again, the separation number, as we've seen in the graph, Ns is equal to rho d square V over 18 mu dB, where dB is the diameter of the barrier. Let's look at this example together. A single cylindrical fiber, 10 mu in diameter, is placed perpendicular to a gas stream that is moving at 1 meter per second. The gas stream contains particles that are 1 micron in diameter, and the particle concentration is 1 milligram per meter cube. What is the rate of collection of particles on the fiber? Now, the maximum possible rate, VdBC, is equal to 1 times 10 to the power negative 5 times 10 to the power negative 3, which is 10 to the power negative 8 gram per meter second. If we catch them all, we will collect 10 to the power negative 8 for every meter of fiber length. The actual amount caught will be the number times the target efficiency. The separation number is equal to rho d square V over 18 mu dV. If we substitute, we'll get the total Ns is equal to 0.617. Now we need to go to the figure again and looking for the cylinders. So we'll go back here, looking for cylinders, and 0.167, I believe it was 0.617. So for this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.61 somewhere here. So for this is 0.4 something, and we'll find that the actual value is equal to 0.42. So we will expect it to, that it collects this amount, the 10 to the power negative 8 times 42%. So it becomes 0.42 times 10 to the power negative 8 gram for every meter second. Another example here, a filter consists of a row of parallel fibers across a flow as described in the previous example, with a center-to-center spacing of the fibers equal to 5 fiber diameters. What collection efficiency will the filter have for the particles? Assume that the fibers are far enough apart that each one behaves as it were an infinite fluid influenced by the other fiber. Here we can use the preceding results to see that 42% of the particles that were traveling directly towards the fiber are collected. If the fibers are spaced 5 fiber diameters apart, the open area is 80%, 5 minus 1 over 5, and the block area is 20%. So for every meter, you will have fiber. This area, which is not the fiber, this is 80%. Now the wide area, that will be 20%. So the target efficiency applies only to those particles that were flowing toward the blocked area. So the overall efficiency will be, now the collection efficiency will be the target efficiency times percentage blocked, which is the 0.42 times 0.2, because now the blocked again is only the 20%. The rest will just flow through the 80%. So now you will get 0.42 times 0.2, which becomes 8.4%. A filter consists of 100 rows of parallel fibers, as described in previous example, arranged in series. They are spaced far enough apart that the flow field becomes completely uniform between one row and the next. So rows really do not interact. What is the collection efficiency of the entire filter? So the eta overall is equal to 1 minus P overall, which is equal to 1 minus P individual to the power of n. This is so we know that the P overall, which is 0.084, but it's 100 of them, so this will be 1 minus 0.084 to the power of 100, which now becomes 0.9998, which is a very good overall removal. Next video, we'll be talking about the scrubbers, and we'll conclude this chapter.